Okay, so I tried to do the Antarctic surface circulation in the last video, and I was running out of time, so I think I kind of did it much more quickly than I should have. Just a reminder, we're talking about convergence and divergence. Convergence is basically when two currents come together, they converge. And what usually happens is when two currents push up against one another, the one that is more dense will sink. Divergence is the opposite. Two currents that are nearby come apart, and water that is underneath can well up into that divergence. So convergence and divergence is responsible for a large portion of the sinking and upwelling of water all around the world. And some of it happens right around the Antarctic. And we need to talk about them real quick because there's a lot more life and primary productivity around Antarctica than you would expect. So the first thing that happens, we're going to talk about the subtropical convergence. And this happens at the edges of, I'm going to do this in green, at the edges of the subtropical gyres. And it's the little red stars in this picture, which is in your book. So where the oceans, the major oceans come down and interact with the Southern Ocean, we have two currents and bodies of water coming together. So there's one here, and here, and here. And basically, the water on this side is warmer, and the water that's on this side is cooler. So what happens is the water that is cooler begins to sink. This water will sink, and this water will ride slightly over the top. And what that causes is some of the masses of water we talked about way back in the beginning of the year when we also did density with the chemistry chapter. That's where you get things like Antarctic intermediate water. That one actually forms here at the subtropical convergence. And then you can get Antarctic bottom water, which happens at the Antarctic convergence. And this water is of intermediate density. It's still cold, but it's not that salty. The stuff in the Antarctic bottom water is very cold and very salty. All right. So that's subtropical convergence. And it occurs in the three major oceans where they interact. So over here we have the Atlantic. Over here we have the Indian. And over here we have the Pacific. So you get subtropical convergence anywhere, and that's because the subtropical gyres interact with the Southern Ocean. All right. The wind blows, remember way back, we talked about the roaring 40s and the screaming 60s and whatnot when we talked about sea surface heights with waves. The dominant wind along as we move towards Antarctica becomes the prevailing westerlies. And the prevailing westerlies sort of blow in this-ish direction, all the way around, and so on. They set off the current we know as the west wind drift. And the west wind drift is more appropriately called these days the Antarctic circumpolar current. It is a circular circulation circuit. Remember that one, Coriot. I think that beats analytical analysis. And it's almost like a gyre, except instead of being empty in the middle, it's got a continent in the middle. And it flows around the entire Southern Ocean. This is actually the largest transport current on the planet, the west wind drift. And what happens there is we now have two masses of water. On this side, this water in here, due to ice freezing and extremely cold temperatures, is very cold and very salty. The water on this side is more typical Southern Ocean water. It's not quite as cold, and it's definitely not as salty because not much of it freezes. So this water on this side is so salty that it goes underneath this water. So we have two areas of convergence. And why do we care? Why do we even break them into different convergences? They look kind of close. Some places are only like 20 or 30 lines of latitude across. It's because they give rise to different masses of water. This one would be the Antarctic intermediate water, and where this one goes underneath is Antarctic bottom water. And in terms of the rest of the ocean and thermohaline circulation, those masses of water end up as layers in the cake if we look at a cross-section, and they actually end up in two very different places. So we want to differentiate where they go, or rather how they're made. Now, we've talked before about the westerlies, and the westerlies tend to blow around. There are also polar easterlies. So in here we would have polar easterlies. they are interrupted at the Antarctic, unlike they are at the Arctic, by the continent itself. They don't blow all the way around like you would expect the way they do in Antarctica, in the Arctic. They set up the opposite current right along the coast of Antarctica that we call the east wind drift. And the east wind drift kind of only really blows in two parts. It blows towards the Larsen B ice shelf, that little peninsula right there, and then from that into the Ross Sea. This doesn't really do much here. It does go around a little bit, but not as much as you would expect. All right, let's back up. Now, remember, Coriolis in the southern hemisphere, which is where we are, is to the left. So if we have a current that is moving this way, Coriolis effect is going to begin to turn it inward. That happens for both the east wind drift and for the west wind drift. So when we're going this way, to the left would be that way, which means that even though the winds are blowing straight, those two currents, let me redraw them, this one begins to curve inward, and this one begins to curve outward. Same thing here, curves inward, and this one curves outward. So we end up with water currents that move away from each other. We call that divergence. And that causes a lot of bottom water to come up, that Antarctic bottom water. This has a big effect on life. This areas of convergence and divergence act as sort of like barriers of different types of species. For example, you rarely find krill north of the subtropical convergence, but you typically find it all over around the Antarctic convergence. They like that cold, nutrient-rich water. In the summer, you find lots and lots of primary productivity near the Antarctic divergence, which is all around here. Whoop, turn the thing sideways. Let's try that again. You find it all around here. Why do you find so much primary productivity there? Well, it's summer, so you have a lot of light. But because you have divergence, all of that upwelled water has lots of nutrients in it. So you get a large amount of diatoms and other cold water planktons that can stand it. So hopefully that helped clear up some of the convergence, divergence stuff. There's a lot in the book talking about specific currents and warm and cold and blah, blah, blah. You should look that over. There's questions about that on the worksheet. But what we really want you to take away from this is we've always sort of drawn the gyres as these like weirdly, as these weirdly perfect, one here, one here. And they're not really that perfect. We put hard boundaries on them, but there's really not any. And the importance of these currents cannot be overexpressed. If we look at the warmth, notice the Gulf Stream sort of hooks a right, kind of here. Let me draw it better. It begins to go this way. And it takes all that warmth with it. If you sort of draw a line of latitude across and look at London versus this part of Canada, this part, these areas have very different climates. And that water that's coming across is still fairly warm. If you notice, some of it gets caught up in the North. Let me erase this again. Some of it gets caught up in the North Atlantic current and swings right by England. And that actually keeps England very, very warm. Some of it comes in here and some of it comes in here. And even Greenland sees a little bit. But it's still fairly warm when it passes England. This is why England is so much warmer than, say, the part of Canada that's at a similar latitude. And it cannot be overexpressed how important surface currents are for keeping the climate warm and able to support life. You can just see, comparing these two, this one has a warm surface current, this one does not. And you can see the difference. Now, an interesting thing starts up here. In this area, this water begins to get very cool. It starts to get salty, just like it does in Antarctica. The Labrador current flows down, also very cold. And the water that forms in this area is what we call North Atlantic deep water. And that North Atlantic water flows along the bottom of the Atlantic Ocean and actually is what starts, is one of the biggest powers of density-driven circulation. It's what causes all of that water to begin to move. This is actually one of the few areas in the Northern Hemisphere where we have any downwelling at all. So it's kind of important. And in the movie The Day After Tomorrow, which we watched, this is the stuff that shuts down. And there's no more downwelling. That water just sits there. And that became a problem because if this doesn't downwell, that equatorial water that comes up doesn't upwell, which kind of shuts down some of this current. And that can be very problematic and basically scary. I know we're getting to 10 minutes, and I'm sorry. I want to talk about the Gulf Stream real quick in terms of eddies. So the Gulf Stream is running along here in red. And on one side, we have cold water. And of course, we demonstrate cold water as green. I don't know why it's this color in the book. And this blue water over here is less cold. So the Gulf Stream, because it's interacting with water that comes down out of these smaller currents, begins to make what we call eddies. And these eddies are little bits, it meanders first. And as it meanders, those meanders begin to pinch off. And if they pinch off and they have to the right, we call them cold ring eddies because they're full of the colder water. And if they pinch off to the left, we call them a warm ring eddy. These warm core rings and cold core rings, or warm rings and cold rings, sometimes they don't use the word core, are really interesting in terms of marine life. See this warm one right here? I shouldn't have used green probably. These things can persist for anywhere from days to months. And months are not as uncommon as you would expect. And these rings sort of move around. And they frequently begin to wander into shore. We get these sometimes in the fall and the winter. And their temperatures can be, at the center of the rings, 10, 15 degrees warmer than the cold water around them. So the cold water that's around them in this ring will, right in here, will provide nutrients, and then the organisms that are stuck in the middle can actually live for a long time. We actually get them where they come into, it keeps doing that, New Jersey fairly often, and that's why sometimes organisms that are inside these rings that hitch a ride, down from Florida, we can occasionally find tropical fish, lionfish, invasive tropical fish, butterfly fish, angels, right here in New Jersey, because those rings peel off and crash into the coast where they begin to break up. That's one of the ways we get the moonfish we catch on the boat. So these rings and eddies, you need to know which side they are. So if they're on to the left of the Gulf Stream, they're going to be warm ring. If they're to the right of the Gulf Stream, they're going to be cold rings. And you just sort of have to memorize that. The last thing we're going to do is just talk very briefly about Ben Franklin. He's the most famous oceanographer. You already knew, even if you don't know he was an oceanographer. And steamships were beginning to move mail around, so were just regular sailing ships. And going towards Europe, those ships made much better times, frequently 2 to 3 weeks less than coming back. And the captains would complain about this. They would frequently have issues with water. The mail would be out of date by the time they made it back. And one of these captains, one named Tim Folger, went to Ben Franklin and was complaining about this. And this got Ben Franklin very interested in currents. So he went around and he talked to all these different captains, and he even made some measurements in himself. And he and his nephew together published a map, the first map of a major current, the Gulf Stream they called it, in 1777. It was mostly the Gulf Stream, and actually included a lot of what we would call the North Atlantic Drift as well. To commemorate this, in 1969, a bunch of scientists got in a little submersible they called the Ben Franklin, and then spent a month floating around in the Gulf Stream, which sounds really boring, but this was a really big landmark in physical oceanography. So I need to know Ben Franklin and his contribution to PhysOcean. So I'm going to stop this video here. We'll do the rest on the next video.